Previously on Learn with Ryan.
Today what we're going to look at is differentiation from first principles. What we're essentially doing is finding the gradient of a particular curve at a particular point. That's equal to, so this time we need to take the limit as h tends to 0 of this function here. So f of x naught plus h minus f of x naught all over h. Hello and welcome to another edition of Learn with Ryan. In today's lesson, what we're going to do is we're going to have a look at how to differentiate polynomials without having to worry about the limit definition of a derivative, what we looked at in last lesson. So first things first, what do I mean by a polynomial? Well, a polynomial is essentially a sum of powers of x or powers of y, whatever variable we're dealing with. So for example, x squared plus 3x plus 4 is an example of a polynomial. Y cubed plus 3y squared plus 2y plus 8 is also a polynomial. Minus z squared plus 3z is also a polynomial. So we're going to have a look at how to differentiate those sorts of functions. Now, if you remember from last time, what we did is we differentiated from first principles x squared, and we got an answer of 2x. And I also left you with an exercise. I asked you if you could differentiate from first principles x cubed, and you should have got 3x squared. Now, can you see a particular pattern that's happening here? So if we just continued, for example, if we had a function f of x equals, and let's say it's equal to x to the power of 4, what do you think the derivative f prime of x is going to be? Well, if we followed the same pattern, what you might have noticed is that what we've done is we've brought the power down to the front. So in this case, with x to the 4, we've got 4x. And then what you might also notice is that we've decreased that power by 1. So instead of x to the 4, it becomes x to the 3. So we've got 4x cubed. And that's no coincidence. In fact, we can generalize it. If we have a function of the form x to the n, so we have a function f of x equaling x to the n, then the derivative f prime of x is equal to n x to the n minus 1. So we bring the power down to the front in front of the x, and we decrease the power by 1. Okay, so let's have a look at an example question. Suppose we've got y equals 5x cubed, and we want to differentiate it. Now, so far, the notation we've looked at for the derivative of a function is f prime of x. However, we're not dealing with f of x here. We've got y instead, y equals. Okay, so whenever we've got y as the subject here instead of f of x, the notation we use for the derivative is dy over dx. So what this means is that we're differentiating our y with respect to x, which makes sense because the variable here is x, isn't it? So what we need to do is we just need to use that formula we've just looked at. So if we've got the function x to the power of n, the derivative is going to be nx to the n minus 1. So in this case, we can see that our power is 3, isn't it? So we need to bring that 3 down. Okay, so essentially what we're doing is we're going to multiply 5 by 3. So 5 times 3 is the first thing we need to do. I just put that in brackets to keep it separate. And then what we do is we decrease the power of x by 1. So then what we end up with is x to the 3 minus 1. And if we work that out, 5 times 3 is 15. So we have 15 x to the power of 2. Okay, here's another example question. Suppose we've got y equals 3x squared plus 4x, and we want to differentiate it. In other words, we want to find dy by dx. So what we need to do when you've got separate terms here, we have to treat them separately. So let's start off with the 3x squared. So again, to differentiate that, what we need to do is bring the power down. So we end up with 3 times 2. So 3 times that power. And then we decrease that power by 1. So 2 minus 1. Next, we've got 4x, so plus 4x. So we need to be able to differentiate 4x. Now, x is just the same as x to the power of 1, isn't it? So again, using that formula, we bring the 1 down. So we end up with 4 times 1. And we decrease that power of 1 by 1. Okay, now when you are answering questions like this, you don't necessarily need to show you working in this form. This is just to help you see what's going on for beginners. Okay, so what we can do next is just multiply this together. So 3 times 2 gives me 6, and then decrease the power by 1. We get x to the 1, or just x. We don't need to write to the power of 1. And then plus 4 times 1 is 4. And then we've got x to the 0. But remember, anything to the power of 0 is 1. So x to the 0 is just 1. So all we've got is 4 times 1, which is 4. So that's a clear rule, actually. If you have just an x here, so x to the power of 1, to differentiate it, we can just remove the x. So differentiating 4x just gives me 4. Differentiating 3x gives me, that's it, 3. So that's my answer. So if y equals 3x squared plus 4x, then dy by dx is equal to 6x plus 4. So let's have a look at a more complicated example. Suppose we've got y equals the square root of x plus 2x, and we want to differentiate it. Now we cannot differentiate it straight away because we haven't written all the terms as a power of x. What we've got is the square root of x. However, in order to be able to differentiate it, we need to write it as a power of x. So you should remember from GCSE that if you have the square root of a number, that's the same as raising that number to the power of a half. For example, if I have 16 to the power of a half, that is the same as saying the square root of 16, which is 4. It's exactly the same here. So what I can do is I can rewrite my y as x to the power of a half. And then I've still got my 2x, which is easy enough. Okay. So now let's differentiate it now that we've got them written as powers of x. So dy by dx is equal to, now this is going to be a bit trickier because we're dealing with fractions here, but it's the same idea. We bring the power to the front, so we have a half, and then we've got x, and then we need to raise that power by 1. So I'm just going to write it in full just to show you what's going on. So we're decreasing the half by 1. And then that's plus, and remember, if it's just x on its own, so to the power of 1, for example, we can just remove that x, can't we? So then what we get is plus 2. Okay, let's just tidy this up a bit. So we've got a half x, and then a half minus 1. If you work that out, you should find you get minus a half, and then plus 2. And that is my answer. Okay, here's another example. So we've got f of x this time is equal to 1 over root x plus 3x squared. So again, we need to write them in terms of powers of x. So 1 over root x. Well, we know that root x is the same as x to the half. So that's 1 over x to the half. And then we've still got our plus 3x squared. Now 1 over x to the half, well, we can write that as a negative power, can't we? So we can, 1 over x to the half is the same as x to the minus a half. And then we've got plus 3x squared. Okay, so now what we can do is we can differentiate it. Because we've got f of x here, we need to write the appropriate notation, which is f prime of x. So just as before, we bring the power down. So we have minus a half. And then what we've got is x. And then we decrease the power by 1. So minus a half minus 1. And then to differentiate this, again, we bring the power down. I'm going to do this in one go. So 2 times 3 gives me 6. So we've got plus 6x. And then decrease that by 1. I just get 1, don't I? So it's just 6x. So when you're answering questions like this, you can just do this without actually showing all the individual steps. So the more you do it, the better you'll get at it, I promise. Okay, so let's just tidy this bit up. So we've got minus a half x, minus a half minus 1. If you work that out, you should find you get minus 3 over 2. And then we've got plus 6x. And that is the answer to that question. Okay, let's have a look at one final example. Suppose we want to find the gradient of the curve with equation y equals x to the 4 plus 3x squared plus 2 at the point 2, 30. So remember from last time when we looked at introducing the derivative, when we find the derivative of a function, we're finding the gradient at a particular point on that curve that the function represents. So this is a typical differentiation problem we're dealing with. So first things first, we need to differentiate that function that we've been given. So let's write that down. So we've got y equals x to the 4 plus 3x squared plus 2. So first things first, in order to find the gradient at the point 230 on that curve, the first thing we need to do is differentiate. So what I'm going to write is dy by dx. So remember what we do is we bring the power down. So we've got 4x and we decrease the power by 1. So 4x to the 3. Here we do the same thing. So plus, bring the power down. So we've got 2 times 3, which is 6, and decrease the power by 1, which just gives me 1. So we can leave it as x. And here we've just got a number, we haven't got an x term. So if you've just got a constant, just a number at the end, and you're differentiating it, then that number disappears. Okay, so when we differentiate, this is what we are left with. 4x cubed plus 6x. So the next thing we need to do is take our point 230, and we want to find the gradient at that specific point. So for that, we need to take our x coordinate, which is the 2, and essentially we just substitute it into this here. So what we can say at x equals 2, the derivative, so dy by dx, is equal to, and then we just substitute 2 into this. So we've got 4 times 2 cubed plus 6 times 2. And then we just work that out. 2 cubed, well, that's 2 times 2 times 2, which is 8. So we've got 4 times 8. 6 times 2 is 12. 4 times 8 is 32. So we've got 32 plus 12, which is 44. and that is the gradient at that particular point on the curve. So that's it for today. I hope you've enjoyed today's lesson on differentiating polynomials. Before I leave, I'm just going to leave you with this question. Can you find the gradient of the curve with equation y equals the square root of x plus 3x at the point 4, 14? Feel free to comment your answers in the comment box below, and don't forget to like and subscribe. And I look forward to seeing you next time when we have a look at finding the equation of tangents and normals to curves at particular points. So I'll see you then. Take care. Bye bye.